term periodic motion refers to any movement sequence that is repeated over a specific interval of time. Simple harmonic motion is a special kind of periodic motion in which we can establish a point of equilibrium and the extreme points of both the forward and the back movements are equal distance from the equilibrium. A common example of simple harmonic motion is a weight bouncing up and down on a spring. In this drawing here, the middle spring is depicting a point of equilibrium. That's the point where, when eventually the spring stops moving, the weight will come to rest. In the meantime, as the spring is oscillating up and down, you can notice that the high point of the spring are both equal distant from the point of equilibrium. We can use the characteristics of all waves to help describe the motion of the spring. The movement of the spring will have an amplitude, which is how high the spring bounces up and down from the point of equilibrium. It will also have a period, which is how long it takes for the spring to complete a full cycle of an up and down movement. To calculate how long it takes for a spring to go through a full cycle of up and down, we can use the equation that the time of a full cycle is equal to 2 times pi times the square root of the mass on the spring divided by k, which is a measurement of how thick or stiff the spring is. You should also be aware of the different forces that help the spring move. Of course, we always have the mass of the weight times gravity pulling us down. That's constant. We also have the force of the spring as it gets stretched out and compressed, and that equation is the force exerted by the spring is equal to the spring constant k times delta x, which again is how far the spring is stretched or compressed away from the point of equilibrium. The spring also has potential energy, and that equation is the potential energy is equal to 1/2 times the spring constant k times how far the spring is stretched or compressed squared. As the spring bobs back and forth, what we're really experiencing is potential energy being transferred to kinetic energy, and then kinetic energy being transferred back again into potential energy, and so on and so forth. As the spring gets compressed, we build up potential energy. Eventually, that potential energy is released as the force of the spring pushes the object down. At the point of equilibrium, that's where the weight has the highest velocity, or the highest kinetic energy, which we describe as 1/2 times the mass of the object times the velocity squared. And as the spring is stretched, the kinetic energy slowly gets transformed into potential energy, which again is 1/2 k delta x squared. And this cycle of kinetic energy to potential energy and potential energy to kinetic energy continues to be repeated. A swinging pendulum is another common example of simple harmonic motion. Just like the spring, we can graph the pendulum's movement in a classic sine wave. While in both the spring and the pendulum, we describe the kinetic energy as 1/2 times the mass times the velocity squared, in a pendulum we describe the potential energy as mass times gravity times height. But the height is not necessarily measuring the height of the object above the ground. Instead, it's measuring the difference in height from its peak swing down to its point of equilibrium. There's also a difference in how we calculate the time it takes for a pendulum to swing back and forth. And that equation is that the time it takes to swing back and forth is equal to 2 pi times the square root of the length of the rod divided by the force of gravity. Note how mass and height are not part of the equation. And that's an unusual fact about pendulums. How heavy the object is and how high you swing it does not change how long it takes to go back and forth. If you push the pendulum up higher, yes, it will have more distance to go back and forth. But because you gave it more height, you also gave it more potential energy, which when it gets translated into kinetic energy means a higher velocity. So this problem describes a mass bouncing on a spring, and they're asking about the period of motion or the time it takes to complete a full cycle. So we're likely going to use the equation that time is equal to 2 pi times the mass of the spring divided by the spring constant k. So we could write the equation that 2 seconds is equal to 2 pi times the square root of m divided by k. Then the question asks, what happens when you double the mass? In other words, they want to know what is the time when 2 pi is multiplied times 2m, we've doubled our mass, divided by the same spring constant of k. So the math looks a little scary, but by using the rules of exponents, it's not going to be that bad. Remember that if I say the square root of 2m, that's the same thing as the square root of 2 times the square root of m. And you should memorize that the square root of 2 is roughly equal to 1.4. Knowing that, we can rewrite our equation as time is equal to 2 pi times the square root of m over k times the square root of 2, or 1.4. And from our earlier equation, we already know what 2 pi times square root of m over k is. That's equal to 2. So by using simple substitution, we can say that our time is equal to our old time of 2 seconds times 1.4, or 2.8 seconds. This question is asking us about the maximum speed of a pendulum. In all simple harmonic motion, the maximum speed is at the point of equilibrium. In a pendulum, that's the low point of its swing. That's where the velocity or the kinetic energy is at its maximum. So we could say that the kinetic energy, or 1/2 times the mass times the velocity squared, is at its peak when the pendulum is at the lowest point. But where did that kinetic energy come from? Well, it had to come from potential energy, and the potential energy is greatest when the pendulum is at its highest point. And that equation is the mass times the gravity times the height. The problem tells us the pendulum is 6 meters above the ground. But that's not our height. In a pendulum problem, we're only concerned about the distance between the high point and the point of equilibrium. The high point is 6 meters above the ground, and the low point, the problem tells us, is 1 meter off the ground, making the distance from the high to the low a height of 5. Now all we do is set our maximum potential energy to our maximum kinetic energy, or mgh will be equal to 1/2 times the mass times the velocity squared. Or in this case, a mass that we don't know times a gravity of 10 times a height of 5 is equal to 1/2 times a mass that we don't know times velocity squared. We do some algebra, the masses cancel out, multiply both sides by 2, and we get 100 is equal to velocity squared, or the maximum velocity is 10 meters per second.